Hello and welcome to Chapter 5. This is Chapter 5 in your textbook. Okay, it's thermochemistry. I'm kind of calling it energy. We have another huge chapter of energy later in the spring, Chapter 19, but this is sort of an introduction to how we handle energy in chemical processes and the ways that we describe it and that sort of thing. So you'll find all this information in Chapter 5, which will certainly be assigned for reading to accompany watching these videos. As we start Chapter 5, it's important that we come to an agreement on the meaning of these four terms. So what I'd like you to do is pause the video at this point and take a moment to define each one of these. Use your book, use the internet, use whatever your little heart desires, but pause the video, look those terms up, and then restart and we'll talk about it. Energy, as you, I hope, have determined, is defined as the ability to release heat or do work. If you have taken physics, you know what work is, okay? Chemistry tends to focus on the heat aspect of energy, although there are some times when we may in fact put both of those together, the heat and the work. But we will focus primarily on the release of heat. Temperature is a relative measure of the kinetic energy of the particles in a sample of matter. Higher energy would be represented by a higher temperature. Heat is defined as a flow of energy from an object at a higher temperature to an object at a lower temperature. You can experience this if you place your hand on the tabletop. It is likely the tabletop feels cool to your hands, but if you leave your hand there for a while, as energy flows from your hand to the table, it feels less cool because of this flow. Thermal equilibrium is the state in which all materials that are in contact with one another have the same temperature. In this course, it'll be important to use these terms correctly and to not get them mixed up one for the other. So take the time to study these, process them, and make it part of your vocabulary. As for the temperature units we will be using in this class, certainly the one you're never going to see is Fahrenheit. We will, for the most part, use the Celsius temperature scale. We may also use the Kelvin temperature scale at some point, okay? Celsius temperature scale has two reference temperatures, 0 degrees, which represents the freezing point of water, and 100 degrees, which represents the boiling point of water, okay? The Kelvin scale is very similar to the Celsius scale. It has those same two reference points, except they are skewed by 273 degrees, okay? And in the Kelvin scale, the lowest temperature is 0, which we call absolute 0. And that lowest temperature in Celsius would be negative 273, okay? The interesting thing about these, though, is because there are 100 units between the boiling point and freezing point in each scale, the size of a degree is the same. what this means is if you calculate delta T, which represents a change in temperature expressed delta T, it makes no difference whether you're measuring the delta T in Celsius or in Kelvin, the delta T would be the same. So as we look at units that are used in this chapter, absolute temperature values, so actual measured temperatures of a stationary system, would not be the same in Celsius or Kelvin. But the delta T for a system that either increases or decreases in temperature would be the same in Celsius and Kelvin. So that will be useful later on. I'm going to take a shot here that you have studied some calorimetry in your previous class. Calorimetry is a method that we can use to determine the energy intake or output of a material whose temperature goes up or down, okay? And it is based upon this equation that you see here. M represents the mass of whatever that substance is that we're talking about. Delta T represents the change in temperature for whatever that substance is, and C represents the specific heat capacity of whatever that substance is. Now, in your textbook on page 179, you will find a variety of specific heat capacity values listed. So it would be a good page for you to put a sticky note on and kind of keep track of so that you can look up values as they become necessary. I do want to point out that there is a difference between specific heat capacity, this value C in the MC delta T equation, okay? That's a value you have used in the past, okay? And it is based upon the amount of energy needed to raise 1 gram of this substance by 1 degree Celsius or 1 degree Kelvin, because that's a delta T. Okay, this is the value you're probably more familiar with. Heat capacity, on the other hand, has to do with a particular object. Okay, you notice this value is just simply energy per degree of delta T. Okay, there is no mass factored into this. There's no grams in this. This is usually assigned to an object, such as a particular pot that you might be using to heat water in, okay? And this heat capacity is predetermined for that particular pot that has a certain mass, okay? It's also used as a heat value for certain calorimeters, because in fact in calorimetry, most of the time the calorimeter does in fact absorb some energy, but its mass doesn't change. So you'll encounter this as we work through some problems. So how about we try one example of solving the Q equals MC delta T equation for this scenario. Okay, read the problem to yourself, pause the video, and give it a shot. You'll find, oh here, let me tell you the heat capacity. Specific heat capacity for iron is 0.45 joules per gram Kelvin. Now pause the video and go ahead and try to solve this. Okay, let's give this a try. The equation is Q equals MC delta T. The mass of the iron is 500 grams. The heat capacity of iron is 0.45 joules per gram Kelvin, and the delta T is 95 minus 25, which is 70 Kelvin. One thing I did not yet tell you about deltas is when you calculate a delta T, okay, a change in temperature, what we do is we take the final temperature minus the initial. A delta is always final minus initial, and if you've had physics, you know what I'm talking about because you've heard this before. So that's why I'm using this equation to find the delta T, and therefore the delta T in this case is a positive temperature change. When we do this calculation, we come up with a value of 1.6 times 10 to the 4th joules. Okay, that is corrected for significant figures. I can only keep 2 significant figures in my answer. My delta T is 2 significant figures, and my specific heat capacity is 2 significant figures, even though my mass is 3 significant figures. So that's the answer as I report it. I could also convert this if I wanted to and report it as 1.6 times 10 to the 1st kilojoules, or 160 kilojoules. So here we are with a problem that is a little more interesting in that it's not just straight calculating Q. So read this one over, give it some thought, give it a shot, pause the video, and then restart when you have had a chance to play with it for a few minutes. So now that you've restarted the video, you can see my work. I'm getting a delta T of 64 Kelvin, which is the same as a delta T of 64 degrees Celsius. Okay, the energy was absorbed. So delta T is positive. So the temperature will have gone up 64 degrees. 29 plus 64 is 93 degrees Celsius. One thing to note here is you were not asked for the delta T, you were asked for the final T. Just read the question carefully.